Yeah, so this is the symmetric part of the velocity gradient, and in initial notation, you have that 1/2 vi partial xj plus vj partial xi, right? And you'll notice, remember we defined the small strain. Remember the small strain, the linear strain, is, partial u, partial x, partial ui, xj plus partial uj, partial xi, right? And so then if I take the time derivative of the small strain, then I'm taking the time derivative of the u's, right? So that's just the v. Right? And so you'll notice that these two things look similar. The only difference is in the denominator, right? In the deformation gradient, we have, it's in terms of the Eulerian x, right? The current configuration. Whereas in the small strain, there is no current configuration, right? In the small strain limit, there's no distinction between the two configurations. There's only the reference configuration. And remember, the relationship is that for x, is equal to x plus u. So for small u, for small displacements, the two configurations are roughly the same. So in other words, what I'm saying is the rate of deformation tensor agrees with the small strain rate, the rate of small strain, the rate of linear strain. Okay? All right, so if you remember, when I started this derivation, I chose to sort of take the time derivative of this. And since now we know how d, we have a definition for d, then let's take the time derivative of this to try to determine what the rate of green strain is. And it'll be apparent soon why we need all these things. Right. So if we take the time derivative ds d squared, where we have d big X transpose 2 dE dt d big X, right? So I took the time derivative, and the only thing I have to do there is take the time derivative of the green strain, because ultimately, if I apply the chain rule to each term, these big X's are not functions of time, so those are just going to drop out. So the only term that lives, that survives the chain rule, is this one, okay? Right? And, we also derived, just now, what we derived was that d little x is 2d. Well, we said that d dt ds squared is equal to d little x 2d dx, right? So since the left-hand sides are equal, the right-hand sides must be equal, okay? We can use our definition of the deformation gradient, right? F dx So you can see that there's a couple formulas. I mean, all this stuff, I know it seems like a lot of derivation and stuff, but it really just starts, remember all we did was draw vectors, right, at the beginning. And we derived some equations, and this being a very fundamental one. And then we get all these derivations, essentially just using that equation and doing some manipulations, right? So if I substitute this in so that I can get everything in terms of d big X, so then I have f d big X transpose 2d f d big X, and then use our little rule again, d big X transpose f transpose 2d f d big X, right? And again, these two things are equivalent, right? Now we have the d big X's there cancel, the 2's cancel, right? So then we have this equals that. So we have that dE dt, the rate of green strain, is equal to f transpose d